Hi, this is Dr. Riley, and in this module we're going to focus on the periodic table and the definition of isotopes. In a related module, we define the atom and elements, and we found that by definition, all atoms of a given element have the same number of protons in their nuclei. This means they have the same atomic number. The elements have been neatly arranged in order of atomic number into the periodic table of the elements. There are many versions of this table that are available in your textbook and online, and it's critical for you to be able to quickly extract information and understand the symbols from any version of the periodic table that you may pick up. In all cases, each individual box contains information about a single element. There is a repetition or periodicity in the properties of the elements, hence the name the periodic table. The periodicity only occurs in one particular direction, however. So the properties of the atoms in the periodic table vary as you go across a row. Each row is called a period, and they're given the numbers 1 through 7. The columns are meaningful too. Each column is called a group or a family. Thinking about your own family, you probably have similar characteristics, and that's why we call these families. Each column has similar chemical properties. The modern periodic table has 118 elements shown, again, one per box, and it's important to be able to look up a particular chemical symbol quickly as you're using this resource. I've drawn for you one box from the periodic table, the one for helium, to try to show you an important point that may surprise you. First of all, you can very quickly find the atomic number in the upper left-hand corner of most periodic tables, and the atomic symbol in the center. The number on the bottom references an atomic mass. You may expect this to be a nice round number, but in fact, if you look at the periodic table, it's not in any case. So let's explore why, for helium, the atomic mass is not exactly 4, it's a little bit larger than 4. Rarely do all atoms in a natural sample of a given element have exactly the same mass. In fact, most elements consist of a mix of atoms with differing mass numbers. Isotopes are variants of an element that have the same atomic number, so they're the same element, but they differ in their mass number. This means that they all have the same number of protons in their nuclei, but the number of neutrons varies from one type of atom to the next. Check out this heap of sulfur, for example. Scientists have discovered that there are 24 isotopes of sulfur. All of those isotopes have the same atomic number, 16. The mass of the various sulfur types ranges from 26 to 49, though. So if you subtract 16 from 26 to 49, you actually find out that the number of neutrons in sulfur isotopes ranges from 10 up to 33. Since neutrons contribute to the mass of the atom roughly as much as protons, you'd expect these isotopes to also vary greatly in their mass. In the case of this particular isotope I've written out here, we have a 32 as the sum of the protons and neutrons. So this particular isotope of sulfur would have 32 minus 16 equaling 16 neutrons in its nucleus. We tend to quickly refer to a specific isotope of an element by its mass number. So as a biochemist, for example, I've worked with the radioactive isotope phosphorus 32, or P32 for short. This is the way I would write it in my notebook. 32 as a superscript preceding the symbol for phosphorus, which is a P. Radioactive isotopes such as P32 are really unstable. Not all isotopes are radioactive or unstable, and in fact, isotopes differ in both their stability and their relative environmental abundance. So to review, two atoms with the same atomic number, such as hydrogen, shown here, with the 1 in red, and different masses, written out in blue, are isotopes of each other. Hydrogen actually has just 3 isotopes, and they're drawn below so you can see the different nuclei. The symbols for the isotopes are on the left and the right provided for you. Let's try to figure out the symbol for the isotope hydrogen 2, which is the one in the middle. The easiest part is coming up with the symbol, which is an H, and then we're going to add the subscript, the number of protons, which is 1, regardless of which type of hydrogen you're talking about. The thing that varies is the superscript. So now we need to look at the mass. The mass number is the number of protons plus the number of neutrons. When we add protons and neutrons in the nucleus of hydrogen 2, we have 2, one of each. So the correct symbol for hydrogen 2 is written out here in green. Let's go back to the periodic table. I've expanded for you a box for carbon. You should now quickly be able to find the atomic symbol right in the center, the atomic number up in the upper left-hand corner, and the atomic mass or weight. In this case, it's 12.011. Most periodic tables will have at least these 3 different components, and they're the 3 aspects of the table that you'll most frequently refer to. For a single isotope, such as, say, carbon-12, which is the one I've shown on the top, the atomic mass is a round number, protons plus neutrons. Carbon-12 has 6 protons, which is shown at the bottom, and 6 neutrons, and when you add those together, you find 12. Now, carbon actually has at least 15 known isotopes. I've shown you 3 of them here as examples. I want to get back to this issue of why the atomic mass is not a nice, neat, round number. In the case of carbon, it's a little bit above 12. The atomic weight of an element is always closer to the mass of the most abundant isotope or isotopes. And again, this abundance comes from nature. So they take measurements of naturally occurring carbon and they calculate a weighted average based on the most abundant isotope or isotopes. Because the masses and abundances of the isotopes are experimentally measured with a lab instrument, different periodic tables will have different variations in the significant figures of the atomic weight, and these do need to be considered when you're looking at significant figures in your calculations. Let's do a little practice with the atomic mass and the periodic table. Looking at just these 3 different isotopes of carbon, which one do you think is probably the most abundant? Well, I just told you it's skewed toward the atomic mass. The atomic mass is just over 12. So my guess is carbon-12 is one of the most, or if not the most, abundant isotope of carbon. Let's try another example. What is the mass number of an oxygen atom with 9 neutrons in its nucleus? At this point, you should be noticing that it's really important to know the difference between mass number and atomic number, and to read those terms very carefully when you're being asked questions. So if you look, again, the mass number is the number of protons plus neutrons for a given isotope. So if you begin by looking for oxygen on the periodic table, and I've shown it to you here on the right, how many protons does it have? That's just up here, its atomic number. So oxygen has 8 protons. To get the mass number, we need to add the neutrons. So going back to the question here, there are 9 neutrons in the nucleus of this particular isotope, so the sum of 8 and 9 is 17 is the mass number for that isotope of oxygen. So a follow-up question is shown at the bottom, which is likely the most abundant isotope of oxygen? And they're asking if it's oxygen 18, oxygen 17, or oxygen 16. We need to go back to the periodic table and look at the atomic weight. It's 15.999. This is the weighted average of the different isotopes of oxygen according to their abundance. Obviously, this number is very close to 16, and because it's close to 16, I would suggest that most likely the most abundant form of oxygen is oxygen 16.